All right. Welcome everyone to another video on machine controls. This video series is specifically on permanent magnet synchronous machines. And last time we talked about uh, creating the position signal, right? How can we create a position signal or obtain a position signal from a dynamic system that you've implemented. So we discussed a couple of different approaches that you can use. Now today I'm going to show you how you can implement the reference frame transformation, specifically in order for you to implement field-oriented control or a rotor reference frame model for a PSM or any motor. Actually, you're going to need to know how to implement this stator reference frame to rotor reference frame transformation. Okay, and there's another video under the motor controls playlist that explains reference frame transformation in detail. So I won't go into a lot of detail in this video. I'd rather touch on what are these different methods and then how can you implement them in Simulink. So that's what I'm going to be talking about today in this video. So if you revisit those lectures, you'll see that there are two methods. One is a voltage invariant and the other one is a power invariant. And we're going to be talking about a voltage invariant method because these implementations, these models and the controls that we are applying will need to have an accurate knowledge or good knowledge or correct knowledge of the voltage signals that are being applied in terms of the stator reference frame, and then how basically in order to know what the exact values are. And the reason is, if you look at power invariant method, since power is voltage times current, there are some scaling factors that comes into the picture that scales the voltages and currents slightly differently when you transform between the reference frames. So since we are controlling current in order to regulate the torque output, we want to know, okay, how does my state reference frame currents reflect on rotor reference frame currents, and we want to have an accurate relationship there, and therefore we're going to be using the voltage invariant method. Okay, it's a little bit misleading. It says voltage invariant method even though we use this to transform currents, but basically it's meaning it's only transforming one variable and not a variable like power which has two variables. Okay, so in order for you to and for us to implement this stator reference frame to rotor reference frame, we have two transforms. One is the forward transform and the other one is the inverse transform. So the forward transform transforms ABC variables or stator reference frame variables that are sinusoidal to rotor reference frame rotor reference frame variables that are DQ0 or typically more or less DC-like during steady state. So, and if you are properly frame aligned, that is, okay, if you are rotating at the same speed, if the frame is rotating at the same speed as the signals, these DQ0 variables are going to look like DC signals when you consider the steady state condition. And for that, we're going to use this relationship. This is a Clark-Park combination. So, and I talk about these in my other videos, so feel free to go take a look at those. And this is exactly what we're going to implement in MATLAB. Okay, and then here you have cosine theta minus 4 pi over 3, sine theta minus 4 pi over 3. This could be cosine theta plus 2 pi over 3, sine theta plus 2 pi over 3. It doesn't make a difference, just the trig. Okay, all right. So that's the forward transform. And when we look at the inverse transform, okay, when you look at the inverse transform, you can see that it's again deriving from the same relationship, but rather you're now converting QD0 variables to ABC. Okay, and in both cases, your position, your theta value is actually very important. Okay, very important, uh, and you will see more of this discussion appearing later down the road. Okay, and then if you are interested in knowing about the rotor reference frame and why it is important for a PMSM, I have a number of videos addressing this topic, so please feel free to go check those out. Now, how do we implement this in Simulink? It's actually very easy. Okay, why is it why do I say it's easy? Here you can see the initial position signal that we discussed, how we can generate the position signal, right? This is the Simulink model that we developed to generate position, and then I'm using this position, this theta, to create three sinusoidal sources. You can see here, it's just basically a script to generate three sinusoidal signals. Okay, three sinusoidal signals, nothing different. Okay, these could be cosines, these could be sines, and depending on what's whether it's a sine or a cosine, your Q or D variables will have different magnitudes. That's the only difference. And again, if your if your frame is not properly zero aligned to the signal's zero location, again you're going to have some differentiation, some variation between Q and D values, and that would be a much more deeper discussion, and I do have more explanation on that in other videos. Okay, all right, so this is how I generate my sine or cosine waveforms, and then here this is the ABC to DQ transformation. Okay, so when you go in here, you can see that I have implemented the same the equations that you saw in the write-up previously, and I'm basically calculating my IQ, ID, I0 based on these ABC quantities using the theta value. Okay, using the theta value. And if I go in here, this shows the waveforms. Oh, actually I had to run the simulation. So if I run this simulation, yeah, should be able to see the three-phase signals along with the position signal that we created. Okay, so now these are in stator reference frame. Okay, and now what we're doing here is we are basically using this position signal, transforming them to the rotor reference frame. Okay, so if I can grab a hold of this signal, oops. Actually, let me try to rescale them. There we go. So you can see here the DQ variables, right? You can see that actually you have three variables, DQ and 0. Okay, you can see those three variables here in my DQ plot. Okay, you can see the three variables. You have one here, and then you can see two here. There's a yellow waveform down there. Okay, so those are the transformed variables using the properly aligned position signal. And then what we're doing here in this third transformation is basically taking those DQ variables and then, or the rotor reference frame variables, and transforming them back to ABC. Okay, this is the inverse transform that I spoke of. And you can see this is the inverse transformation implementation. Okay, this is the same the matrix that you saw before. And once you do that, you'll get again the sinusoidal signals that you originally injected. Okay, so you're going from ABC 3 sinusoidal to DQ0 here, and then from DQ0 again back to ABC. So these are the two transformations that we will be using when we analyze, when we simulate PMSMs, as well as when we implement field-oriented control. Okay, I hope this was helpful, and we're going to be talking about more on this topic in terms of PMSM and therefore C control soon. Thank you.